Good morning, everyone. Thank you for joining. This morning, I'm delighted to introduce Professor Christopher Wolverton, who is the Jerome Cohen Professor of Material Science and Engineering at Northwestern University. Before joining the faculty, he worked at the Research and Innovation Center at Ford Motor Company, where he was group leader for the hydrogen storage and nanoscale modeling group. Christopher received his Bachelor's of Science in Physics from the University of Texas at Austin, his PhD in Physics from the University of California, Berkeley, and performed his postdoctoral work at the National Renewable Energy Laboratory. His research interests include computational studies of a variety of energy efficient and environmentally friendly materials via first principle atomistic calculations, high throughput and machine learning tools to accelerate materials discovery, and multi-scale methodologies for linking atomistic and microstructural scales. He is a fellow of the American Physical Society and the American Society for Metals, and he is an ISI highly cited researcher. He has published more than 400 papers with over 40,000 citations and has an H-index of 100. Without further ado, Professor Wolverton.
Okay, thank you very much. I'm assuming everybody can see my screen and you can hear me. Everything's okay?
Yes, we can see your screen, hear you well.
Okay, fantastic. All right, so thanks very much for the kind introduction and the invitation to speak today. You'll see from the title, sort of a provocative title, that I'm going to tell you about the phase diagram of everything, or at least try. And I should start off by acknowledging the former students and postdocs from my group who did most of the work. In particular, I want to acknowledge Vinay Hegde, who's now at Citrine, but the others that you see there as well. And some of the work that I'm going to talk about, particularly at the end of the talk, was done in collaboration with researchers at Toyota Research Institute, in particular, Murat Aykal. Okay, so let me get started. Make sure I can change the slides. Okay, so I wanted to just show one slide about kind of generically what my group does, just to give you a sense. My group, so I'm in the material science department at Northwestern. My group is computational in nature. We do almost exclusively atomic scale calculations, mostly based on density functional theory. For those in the audience who don't know about density functional theory or DFT, don't worry, I'm not going to talk about the method very much. I'm just going to use it as a tool for this talk. But we use this kind of quantum mechanical atomistic based tool to study a variety of different problems. And my own particular interests are in energy related applications. So we tend to drift towards a lot of energy problems. So right now we have kind of a fairly concentrated effort in my group in the field of thermoelectric materials. We also are working a little bit these days on lithium-ion battery materials, mostly on cathode materials. A more recent but kind of larger effort that's emerging in our group is that we're collaborating with the Merkin group here at Northwestern. They have the capability of growing sort of mega libraries of multi-component nanoparticles. And we're working with them very closely in that area and specifically focused on catalysis applications. Up here at the top, you see structural metals. So my own PhD and postdoc, although it was a long time ago, was in the area of metal alloy phase diagrams. You'll see some of that today. And basically, so I oftentimes say, so my heart is sort of still in structural materials, and so we work on this as much as possible. And probably the largest effort that we have in the group is this top effort here on high throughput and machine learning, and specifically using that for materials discovery. So this is, in some sense, one of the areas I'm going to talk about. is this top area. I'm just showing this just in case, there are other other areas that you have interest in, feel free to ask me questions. Okay, I oftentimes start with this kind of provocative slide for the students, show this article. This is an article from Barron's. You can see the date here, 2019. So not that long ago. And the title, 3 technologies that could create trillion-dollar markets over the next decade. So trillion-dollar market is not an easy thing to achieve. So you might think when you see an article like this, well, surely I know what those 3 technologies are. There couldn't possibly be a technology that's so big to create a trillion-dollar market, and I've never heard of it. Well, I think that's true. And 2 of them, after I tell you what they are, you probably will shake your head and say, yeah, that makes a lot of sense. So one of the technologies they quote in this article is the CRISPR gene editing technology. So I think that makes some sense. The second technology they mentioned here is quantum computing. And I think maybe that also makes some sense. The third technology, which you may not predict so easily, but maybe you can predict because I'm showing you this slide, is a technology they actually don't have a very good name for in the article. I think in the article, they actually just call it material science. But it's clear from the article what they mean is data-driven materials discovery. So finding new materials using data-driven techniques. So this is, kind of eye-opening, the thought that that you might imagine this kind of technique to be a trillion-dollar market. That's really saying something. Okay, so how in the world can we use data? I'm not going to show you how to make a trillion-dollar market, but I am going to talk about how we can use data to accelerate the discovery of new materials. This is actually a fairly old slide, but still gives a fairly good kind of 35,000-foot overview of the aspects I think you would need to create a platform where you could discover new materials from data. So first of all, you'd have to create data in the first place. And in my group, since we're a computational group, this means we would have to compute properties of many materials, right? That's how we would compute data. I'm not going to talk about this bottom box here, by the way, but one of the inputs to doing DFT calculations is you need to know the atomic crystal structure. You need to know sort of where to place the atoms. And if you want to find new materials, you actually have to have methods to solve for unknown material structures. Anyway, like I say, I'm not going to talk very much about this today, but just to let you know that that's part of the data creation as well. So once you've calculated a bunch of properties of a bunch of materials, you need to kind of collect and classify this information into a searchable database. And then you basically need to, somehow use this data for discovery. And I think there are sort of 2 generic ways you might imagine using this data. One is what I would just call the direct search approach, where you literally just look in the database and you screen through materials in the database to search for the combination of properties that you're looking for. In some way, this is kind of like the Google search version of materials discovery. And we use that. I'm going to show you an example of that. We use that kind of approach all the time. But there are many cases where that approach doesn't work very well for a variety of reasons. And we have to do something more clever than just sort of search for the material in the data set. So we actually maybe are looking for a material that has certain properties, and maybe those properties are not things that we can easily compute. So we can't just sort of look for them in the data set. So for example, if you're looking for the next high temperature superconductor, but superconducting transition temperature is not one of the properties to calculate, how do you find a superconductor? Well, one way to do that is to look not for the superconducting transition temperature itself, but to look for properties that correlate with that transition temperature. If you could find properties you did calculate that correlate with the thing you're interested in, that could be just as useful. And this is where machine learning and data mining approaches come into play. Okay, so I want to tell you a little bit about kind of how we've been going about this database effort, constructing databases, and how we search it in these 2 different kinds of modes. The database that we've been sort of constructing over the last decade, basically, in our group here at Northwestern is called the OQMD, or Open Quantum Materials Database. It's a high throughput computational database. It's a database of density functional theory calculations. So this is calculated properties of materials, not experimental. And I said earlier that one of the inputs, basically all you really need to know about DFT, if you don't know anything about this, is that you input an arrangement of atoms in a periodic box, and DFT solves for the electronic states of this, and you can derive all sorts of different properties. And the main property I'm going to talk about today is the energy of that collection of atoms in the box. Okay. So to construct a database like this, you need to have a large scale collection of crystal structures that you can use to, calculate these properties. And so we start with the collection of crystal structures that are experimentally known. Most of these are collected in a database called the Inorganic Crystal Structure Database, or ICSD. And so we simply go to the ICSD, and we look up sort of every possible inorganic solid that's been synthesized and well characterized, and we know the crystal structure very well. And we make a list of all these compounds and say, can we compute all of the compounds in this data set? And the answer is yes. There's roughly speaking around 50,000 entries in the ICSD that are sort of easily calculable from DFT. And 50,000 calculations is a reasonable number these days that you can do. Okay, so by the way, I feel like I should tell you a little bit of a story that this is a dramatic shift since the time when I was a graduate student. When I was a graduate student, typically you would do calculations 1 or 2 or 3 at a time, and publish a paper on 1 calculation, 2 calculations, things like this. I tell my students now, basically those days are gone. You can't do that anymore. And we've kind of flipped this whole problem and said, well, instead of calculating materials 1 or 2 or 3 at a time, could we just calculate all known materials and store them in a data set and be done? Okay, so that's part of the OQMD, is this 50,000 experimental compounds. But the nice thing about DFT is that there's nothing that requires you to do calculations of experimentally observed arrangements of atoms. Right? You can put any arrangement of atoms in a box and calculate its properties using DFT. And so in addition to these 50,000 experimentally observed compounds, we have a large number of what I call hypothetical inorganic crystalline compounds. And generally speaking, what this means is that we take some common crystal structure like rock salt, for example, and rock salt has a cation site and an anion site. And if you decorate those 2 sites with sodium and chlorine, you form sodium chloride and in the rock salt crystal structure, right? Makes sense. But there's really nothing to prevent you from taking that crystal structure and decorating every possible permutation of elements from the periodic table, right? You could, if there are basically 100 elements in the periodic table, the number of possible ways to decorate rock salt with elements would be 100 choose 2, which is about 5,000. And so you could do 5,000 rock salt calculations and store them in your database. Now, some of you might be thinking, well, that sounds like kind of a silly thing to do because yes, you would occasionally hit upon a reasonable chemistry like sodium and chlorine, but you would do a lot of calculations that make no kind of chemical sense or no physical sense, right? You would do calculations of plutonium and xenon in the rock salt crystal structure. And this doesn't seem to make any sense. So I would say to those who are thinking that, first of all, you're right. There's going to be a large number of cases where we're going to do sort of unreasonable chemistries. But I would ask you to kind of suspend your disbelief for the moment because of a couple of reasons. One is that when we choose these kind of crazy chemistries that don't make any sense, generally DFT is going to tell us that the energy of that compound is very high. And so we're basically going to ignore it in most of what I'm going to talk about later. The other thing that's actually useful about these hypothetical compounds is that they actually, these kind of crazy chemistries are actually very important and helpful in training machine learning models. So machine learning models, if you want to teach a machine about what makes reasonable chemistry, you actually have to give it examples of reasonable chemistry, but you also have to give it examples of crazy, unreasonable chemistries. And so these hypothetical compounds actually essentially serve as negative data that help us train machine learning models. Okay, So this database we have basically about 1 million compounds in it at the moment. It's always growing all the time. It's open and available online at OQMD.org. You feel free to play around with it. We have an API you can use there on the site, or you can just download the whole database yourself. There's a large number of things you can do with a database like this, but the thing that I really want to talk about today is the calculation of phase stability. This is something we can do with a data set. Okay, so I said that there's a couple of different ways that you might think of using data like this to find new materials. The first one was the one I called kind of the direct search or the screening approach. The idea here is very simple. The idea is that you might have some large number of candidates for a given application in your data set. Maybe even the entire database might be considered candidates. And then you devise a set of progressively hard to achieve screens. And so that you can use these screening criteria to sort of, screen down the number of candidates. And hopefully at the bottom of this screen, if you've designed your screen appropriately, at the bottom, you only have a handful of promising candidate materials that satisfy all of the screens for a given application. Okay, so this kind of approach is, like I say, widely used by our group and by others for a variety of different applications. Like I say, I'm not going to belabor it too much, but I do want to talk a little bit about one particular tool that we can use to analyze data in a database like this, and that is the calculation of thermodynamic stability. And to do that, I have to explain to you something called the convex hull. So for those who know what the convex hull is, you can go to sleep for about 1 minute. I'm just going to explain this. This is going to become so central to the rest of the talk that I just need to make sure everybody's with me on this. So, okay. All right. So suppose you're interested in a binary system composed of 2 elements, A and B. You might then go to the database and you might say, okay, tell me all the compounds you have in the database that have these 2 elements, A and B. And I'm going to make a plot of the energies of those compounds. On the y-axis here is the energy, and on the x-axis is the composition of A in the material. Okay, so pure A is going to be over here on the right, and pure B is going to be over here on the left. Okay, so suppose I look up the data in the database, and there are 4 entries that have these elements. Okay, so I have pure A over here, I have pure B over here, and there's 2 compounds here. All right. So you can see from the energy. So by the way, typically we plot what's called the formation energy. The formation energy is the energy of the compound relative to the phase separated elements. So the formation energy of the elements is by definition 0. That's why there's 0 here on this plot. And in this particular cartoon, these 2 compounds have formation energies that are negative, you can see here. And that means that the compounds are stable with respect to decomposition into the elements, right? That's what a negative formation energy is. So this is nice, right? It means that's a good sign for stability. But if you think about it, being stable with respect to decomposition into the elements is a necessary but not sufficient condition for stability. What's sufficient for stability is that the compound actually has to be lower in energy than not just the elements, but it has to be lower in energy than any linear combination of any phases you know of. Okay. So if you ask yourself, if these 4 phases were the only phases in the system, at every composition, what's the lowest energy linear combination of these 4 points? Well, the answer would be this piecewise linear line that I have drawn here. This is called the convex hull. Okay, so the convex hull basically tells you then the lowest energy combination of phases at any given point. It also tells you which phases are stable. If a phase is on the convex hull, it's stable. If it's not on the convex hull, it's not stable. And then the other thing that the convex hull tells you is that the lines that connect points are tie lines and indicate stable 2-phase equilibria. So for example, there's a tie line connecting this phase AB with AB3. That means you can form a stable 2-phase equilibrium between these 2 phases. But for example, there is not a tie line connecting this phase AB with pure B. So even though both of these phases are themselves stable, If you form a combination of these two phases, there's no tie line, so they will not form a stable two-phase equilibrium, but they will react and form this phase, which is lower in energy than the line connecting AB and B. Okay. So now the other thing you can do is you can use this to search for new phases. So suppose you're interested, you think that there might be a new phase in this system at this composition, A3B. Well, this is the currently known formation energy. This is the lowest energy linear combination of phases that we currently know. And so basically this is your target you need to beat in order to find a new thermodynamically stable phase. So if you do a calculation of a new phase and you find something up here, well, it's got a negative formation energy, but it's not on the convex hull. So sorry, you haven't found anything that's thermodynamically stable because this combination of A, B, and A is still lower in energy. On the other hand, if you find something down here, congratulations. Oops, where's my mouse there? Find something down here, congratulations, you found a new stable phase. And now you need to redraw the convex hull, right? So now the convex hull will go from B to AB3 to AB, now down to your new phase, and then back up to A. Okay, so hopefully that's all clear. I gave a very simple example of a binary system because this is a simple, it's easy to sort of graphically show you this. It's just a two-dimensional plot. There's one compositional degree of freedom and energy. And so it's very easy to show you the convex hull in this case. Okay, so if you go to a database like OQMD and you ask for these convex hulls, you can search for essentially any number of components. You can query for a binary system, but also for a ternary or quaternary or even higher. If you query for a binary system like iron silicon, you might see something that looks kind of like the cartoon I just showed you, right? A convex hull that shows you the phases that are stable on the convex hull that are in green here. You see some phases here that are red that are above the convex hull. These are sort of the phases that happen to be in the database. Some of these might be some of those hypothetical compounds I mentioned. And these are phases that are in the database for whatever reason, but are not on the convex hull. But like I say, you sort of can see what's on the hull and you can see what's connected to what. If you go for a ternary system, well, now the dimensionality of the problem just grew by one, right? So for a ternary system, there's two independent compositions that you need to specify. And the two compositions plus energy would make the convex hull a three-dimensional object for a ternary system. It's a little bit clumsy to look at a three-dimensional object. So typically this is plotted as a projection in a Gibbs triangle where the energy scale has been projected out now. But you still see essentially the projection of the two-dimensional composition here. You see the phases that are on the convex hull. You see the tie lines connecting phases on the convex hull. And in this particular plot, you also see phases that are in red that are not on the convex hull. Okay. By the way, in a ternary plot, you also see regions, triangles here. Those triangles are three-phase regions, right? Where you have stable equilibrium between three phases. Okay. Now the question is, what happens if you go beyond that? You go to quaternary or higher order systems. To be honest, it's relatively easy to calculate these convex hulls for higher order systems. It just becomes progressively harder and harder to show them to you because they become these high dimensional objects. So if you type in a 5-component system, in this particular case, copper, nickel, zinc, aluminum, oxygen, the convex hull is a 5-dimensional object, so I don't know how to show it to you. So OQMD will just show you a graph representation, right? So this is a graph of the convex hull. The points are still the compounds that are on the hull. The tie lines are still representing two-phase equilibrium. But the location of the points here now doesn't mean anything. So, all right. So there's all sorts of interesting things you can do with this, searching for compounds in multi-dimensional spaces and so forth. Another thing you can do with this is you can search not just for the convex hull of a given system, but you can search by composition. You can actually input a given composition and say, what is the stable equilibrium? What is the lowest energy linear combination of all 1 million phases you have in your database at this composition? Okay. So one time I was talking with with a student about this. And when I said this, you could type in a composition and query for what's the lowest energy combination of phases. She said, "Oh, that's interesting. You could type in the composition of the Earth's crust." and see what's the most stable collection of phases. I thought that was a great idea. So that's what, basically that same afternoon, that's what I did. You can look up very precisely the chemical composition of the Earth's crust. We know basically the elements that are in the crust and more or less what their composition is. I just took the top 8 elements. Okay, so this is not all of the elements in the crust, but the top 8 more or less form a stoichiometry or a composition, something like this. So the question is, what if you type in this 8-component composition into OQMD and you query for what's the most stable collection of phases? Well, this is what you get. You get a collection of 8 different phases. And you can see what they are here. And I realized almost immediately, as soon as I did this, that, well, I don't know anything about geology. So I have no idea whether this is reasonable or unreasonable or what. Okay. So basically what I could see from looking at this is that there's a lot of silicates here, right? You see SiO4 here and here, Si308 and so forth. SiO2 was probably about the only thing on the list that I recognized initially, right? That's quartz. But basically, other than this one magnesium iron oxide, basically everything is a silicate on this list. So I thought, well, okay, I have to find out whether this is reasonable or not. So back to Wikipedia, and you know, what actually is in the Earth's crust. Sorry, I'm having a little bit of a drama here. There's a crow right outside my window that has seen its reflection in the glass and has decided to attack the glass of my office. So, sorry if I sound a little distracted. I'm trying to ignore that. Okay, so back to this problem. So what is actually in the Earth's crust? If you look online, the answer is 90% of the Earth's crust is composed of silicate minerals. That's great because that's what we saw. And then, the lists are given here and they're given in terms of their mineral names. I translated their mineral names into chemical formulas here. You see the most abundant are things like sodium aluminum silicate, calcium aluminum silicate, potassium aluminum silicate, and so forth. Now, it's interesting if you look back at the prediction that we got from the OQMD convex hull, it's essentially exactly these compounds. Okay, so sodium aluminum silicate is here, and on the convex hull it's here. Calcium aluminum silicate is here, it's over here, and so forth. Okay, and even the percentages actually look pretty good. Okay, so I don't know if this is impressive to you or not, but to be honest, for me this was pretty impressive because for a couple of reasons. One is that this database was not designed with this problem in mind at all. So it certainly didn't have to work. And the other thing, of course, is that the convex hull is a zero temperature, equilibrium answer to what's in the Earth's crust. And of course, the actual minerals in the Earth's crust don't have to be the T = 0 equilibrium state, right? So, so the fact that this kind of works as well as it does is, well, I guess the other thing that I should say is that, this is a complicated 8-component phase stability problem. And again, it's not immediately obvious that that would actually even work for it. So, okay, so that's interesting that kind of thing even works. All right, so let me go on now with that idea in mind. The next part of the story comes from a few years ago when I was reading a book by Jeffrey West called Scale that was recommended to me. It's a fantastic book, by the way. If you haven't read it, I would highly recommend it. The book talks about all sorts of different phenomena and how they can be analyzed in terms of their scaling behavior. In other words, how many different cases pop up that can be analyzed in terms of power law or scale-free power law behavior. And you can see from the title of the book, there's a wide variety of different applications here, from how organisms evolve and the lifespan of organisms to how companies are structured, how we design cities, all sorts of different applications in this book. And I have to say, I was struck by the breadth of the applications in the book, and I kept turning the pages every chapter thinking, okay, when is chemistry or material science going to come into this story? And it never did. I was pretty disappointed by the end of the book because I thought, oh, that's impossible that this kind of way of thinking about problems is so universal and yet not applicable to material science. Okay, so the question is, could we apply this kind of thinking in material science? And I think with the advent of these kind of large-scale databases, the OQMD is just one that I talked about, but there are others as well, like Materials Project and AFlow and so forth. It gives us the possibility to kind of think about material science in a different way than the typical paradigm that we're taught about, where we sort of analyze things from a bottom-up approach of processing structure property. With these databases, we might actually think about analyzing material behavior from a more top-down perspective and analyzing it in terms of a network of materials. Okay, so if we want to do this, the first question is, how do we actually make a network of materials? All right. So you probably already have a pretty good guess of this because I've spent so much time talking about convex hulls that convex hulls are going to come into the story. And if you think about phase diagrams that we learn about in classes, right? The phase diagram over here on the left is the nickel aluminum phase diagram. And we all are taught sort of how to read these phase diagrams. We have different solid state phases here. We have a liquid phase up here. The single phases are in blue. And then we have white regions that are the two-phase regions connecting different phases of the diagram, right? And so this starts to sort of sound like a network, right? We have a collection of phases in this diagram, and we have, ways of connecting those phases via the two-phase regions of the phase diagram. Okay, in a ternary phase diagram over on the right, this is the titanium nickel aluminum phase diagram. It's kind of the same thing, right? We have single phase regions indicated here. We have white two-phase regions that connect these single phase regions. And then in a ternary diagram, we even have more information. We have three-phase regions that are indicated here. I think that's yellow. Okay, so the phase diagram is in some sense a network representation of material science, and I want to sort of exploit that. But for my DFT database, I can't easily get the full composition temperature phase diagram. I can get these convex hulls, the T=0 sort of isothermal section. Okay, so the convex hulls, like I showed you examples of binary and ternary systems, they are, again, networks in the sense that if we think of the nodes of the network as the stable phases that are on the convex hull, and the edges of the network as the tie lines that connect phases on the convex hull, then both of these kind of phase diagram graphs can be thought of as a network. Okay, great. So we can actually represent T=0 phase diagrams or convex hulls as networks. And we can do this not just for binary or ternary systems, but higher order systems as well, 4-component or even higher. And like I say, when you get to these large scale representations, the dimensionality grows at such a rate that it becomes very difficult to visualize. But nevertheless, it's easy to compute. So I think that this image over here is actually like a 10 or an 11 component convex hull. I think this is all the 3D transition metals plus oxygen. And you see here basically now in this kind of graph theory representation of the network, the nodes again are all of the compounds on the convex hull. The dense collection of tie lines is so dense you can barely see are the two-phase regions, and the size of the points actually in this case now represents how many different tie lines is coming out of each node in the network. Okay, so you could get a sense of the connectivity of each material in this network in terms of the size of the symbol. Okay, so let's do a little bit of a thought experiment here, and let's take this binary, ternary, quaternary pathway to its extreme. Okay, I've told you a couple of things in this talk so far. I've told you that an n-component system has a convex hull that's n-dimensional. And I've also told you that we can compute convex hulls for essentially arbitrary number of components. Okay, so what if we take the maximum value of n? the maximum possible value of n, the number of components in the system, is the number of elements in the periodic table. It's physically impossible to have a, mathematically impossible to have a phase diagram of higher dimensionality. Okay, so if one could construct a phase diagram that was n-dimensional, where n was the number of elements in the periodic table, and just for the spirit of discussion, let's just assume that the number of elements is around 100, this phase diagram of everything would be a 100-dimensional object, would be a 100-component system. And in some ways, if you think about this, there's only one of these phase diagrams, right? There is just this one 100-dimensional phase diagram, and every phase diagram you've ever seen in your life is just a section through this, right? It's a, it's a much lower dimensional section. Okay, so like I say, we can compute this 100-dimensional phase diagram of everything from OQMD. We can calculate all of the compounds that are on the convex hull and all of the tie lines. But like I say, it's a 100-dimensional object, so I can't show it to you in any reasonable way. Okay, so all I'm going to do is just tell you that we've computed it and then tell you properties of this network, okay? Because I really just have no way of showing it. Okay, so we analyzed the topology of this network after computing it. It turns out that it's a network with about 20,000 stable inorganic compounds. So there's about 20,000 compounds on the convex hull. So by the way, 20,000 out of 1 million. So being on the convex hull is sort of relatively rare for the data in the data set. And there's about 40 million tie lines. Okay, so this means that 40 million two-phase equilibria and roughly 20,000 stable compounds. It turns out that this network is extremely highly connected compared to social networks or other kind of networks that network theory people tend to study. Each material has a tie line with about 20% of all other materials. So this means if you choose a compound at random, it's going to form stable two-phase equilibrium with about 20% of all other compounds known. And for about 80%, what it means is there won't be stable two-phase equilibrium. Those compounds would react and form something else. Okay, we can also form calculate what's called the mean node degree. The mean node degree is just the average number of tie lines that come out of every given compound in the network. On average, it's about 3,850. And what this means is that on average, every stable inorganic compound forms a stable two-phase mixture with about 3,800 other compounds. Okay. A couple of other kind of interesting topological features of the network. You can analyze the sort of diameter of the network. This is like analogous to the 6 degrees of separation that you've probably heard of, that sort of all human beings on Earth are related to one another by 6 degrees of separation of friendships, right? You can connect any person to any other person with 6 steps. So for our materials network, what is that number 6? It turns out that it's actually very small. It's less than 2. So this means that every compound is connected to every other compound by jumping less than 2 times through the network. And you might wonder, why is it so small? Why is this network so densely connected? It's densely connected because there are hubs in this network. So there are things like the noble gases, but there are other examples of this as well. The noble gases form an intuitive example of this, where you would expect the noble gases don't react with anything. So they're essentially going to form stable two-phase equilibrium with everything in the network. So they're going to have the noble gases are going to essentially have a tie line with everything in the network. And so if you think about this, then if you have 2 compounds, you can always jump from one compound to a noble gas and then the noble gas to the second compound, right? So there's almost always a pathway. Well, there's always a pathway where you can get from any compound to any other with 2 jumps. And then, like I say, the network itself is quite connected, where there's 20% of all possible combinations that actually can be directly connected. So 20% of the time you can reach the other compound with just a single jump. Okay, so this, by the way, this makes this network extremely dense and extremely interconnected, again, compared to social networks. Again, going back to this idea of every material having a tie line with 20% of all other materials, the social network analogy of that statement would be like if in Facebook you were friends with 20% of all other people on Facebook, right? I mean, obviously no one is friends with 20% of all the people on Facebook. And so, you know, this is a much more densely connected network than the typical social network. We can also calculate something called the global clustering coefficient. The global clustering coefficient just tells you if you have two compounds that are both connected to a third compound, what is the probability that those two compounds connected to a third, what is the probability that those compounds themselves are interconnected? Okay, so it tells you something about the sort of clustering, and again, this the clustering coefficient is 0.5, and what that means is much larger than a random network at the same density. So again, the bottom line is this is a very highly connected materials network. We can do more sort of analysis of the topology of the network. This is a plot of the fraction of different nodes. Again, remember, nodes mean compounds, and the node degree is the number of tie lines coming out of each compound. And you see a log normal distribution here of materials in the network. So this is, again, different from social or technology networks. You also see a heavy tail here. You see a relatively small fraction of very highly connected compounds. Like I say, these are essentially hubs in the network. A small fraction of things that are have a very large number of tie lines coming out of them. Other things you can do, you can look at sort of the mean neighbor degree. So you can look at for a compound, you can plot not only its node degree, the number of tie lines coming out of it, but you can actually look at the node degree of the neighbors of that compound. And you see here essentially a behavior here where the compounds that are highly connected in the network are actually connected to ones that actually have a sort of low node degree. Okay, so what this behavior is called dissortative. It means that materials in the network are connected to those with actually fewer tie. Highly connected materials are connected to materials in the network with lower number of tie lines. We also see things like highly connected communities. So there are sort of very highly clustered compounds that have a very high clustering coefficient and sort of relatively low mean node degree. These are materials that are themselves within the community are sort of interconnected quite well, but they're not connected very well to the rest of the network. Okay. So anyway, you can kind of go on and analyze this kind of behavior at great length. But in the last, say, 5 minutes or so, I want to tell you about a problem that I'll tell you two things. One is that how we could extract new information from this network, not just sort of analyze topology and just say, oh, that's interesting. But we actually extract from this now something that we call the nobility index. So if you're with me so far and you agree with me that sort of tie lines coming out of a material are indicative of a material that has a lot of stable two-phase equilibria, and hence a material that's not very reactive. So for example, I said noble gases essentially have tie lines with everything in the network, so they're obviously not very reactive. And so maybe the number of tie lines coming out of the network is in some ways a measure of the nobility of a compound or the inverse reactivity. And so we made this kind of purely data-driven general nobility index, which is essentially the z-score of the mean node degree. It's essentially the logarithm of the number of tie lines coming out of each node minus the average divided by the standard deviation. So a positive score for this means a very highly noble compound, and a negative score means a very reactive compound. And you can actually define this not just for elements, but for all the compounds in the material in the network. But here's the nobility index for the elements. And you see some things that are pretty interesting. You see some things that are fairly intuitive, like noble gases have a very high positive score, meaning they're very noble. And you see things maybe also that make sense, like fluorine having the most negative score, meaning fluorine is sort of the most reactive element in the periodic table by this metric. You see copper, silver, and gold, the so-called noble metals have a fairly high and positive score. But gold, by the way, is not the highest, which is kind of interesting. People have long thought that gold was the most noble metal. Silver actually has a slightly higher score here. And you see some other maybe non-intuitive things like the alkali metals. You might think of them as very reactive, but by this score, they actually have a fairly large and positive score. I mean, they're sort of relatively noble by this index. Okay, so the last thing I want to tell you about is how can we actually use this in some, to say something about the computational discovery of materials. So there's many examples of materials now that have been predicted by computation in the literature. Papers that predict these things are coming out all the time. What generally speaking, we don't do very well as computational researchers is tell our experimental colleagues how to synthesize these new predicted compounds. We just say, we've predicted a new compound, we've screened it for stability, it's thermodynamically stable, so we think you should be able to make it. Our experimental colleagues always say, great, how do we make it? And then we have to sort of shrug our shoulders and say, well, we don't really know. So one of the reasons why this is not easy to do is because it's so challenging to predict synthesis, right? I mean, it's such a complicated story, depends on not only thermodynamics and kinetics, but also, kind of intangible things like, does this experimental lab have the necessary precursors or expertise? Is there funding in this area that people actually have used to actually synthesize materials and so forth? So it's very difficult to sort of kind of predict all these things in a reasonable way. And what we've tried to do here is, rather than trying to predict the synthesis recipe for a given compound, we wondered whether we could use this network analysis to predict the likelihood that a material could be synthesized. Okay. So again, the synthesis recipe itself is complicated, but maybe we can analyze this network and say something about the likelihood of a newly predicted compound to be synthesized. And the trick here that we're going to use is, I told you that many of the compounds in our network come from the ICSD. So they're experimentally observed compounds. And not only that, but the ICSD actually tells us the year in which these compounds were discovered. So that means that if we restrict our network for the moment to only ICSD compounds, then every node in our network actually has a timestamp associated with it. And that's the timestamp associated with when that compound was discovered. And so what this means is that we can actually watch the convex hull or this network evolve in time. We can sort of rewind time and say, what did the network look like in 1973? Or what did it look like in 1989? So forth. Okay. And so when we do this, we can actually analyze the kind of number of nodes of the network and the number of tie lines in the network as a function of year and things like this, which is very interesting. And I could talk for a long time about this. But what I really want to do is tell you about, could we look at the topology of the network and get a clue from the topology of the network as a function of time that a new compound was about to appear in the network. In other words, if we look at the part of the network where YBCO appeared at some point, the question is, could we have sort of seen from the topological features of the network that a new compound was about to appear in that part of the network? So what we've done is built a machine learning model of this property, which we call the discovery timeline. The discovery timeline is essentially 0 for a given compound before the year of its discovery, and then it's 1 after that. And we built a machine learning model where the descriptors of the model are essentially these topological features of the network that I've talked about, the mean node degree and the clustering coefficient and all of these kind of topological features. And we've used this to design a machine learning model that predicts this discovery timeline for a given material. Okay, so in cross-validation, a random forest, kind of a relatively simple machine learning model, achieves greater than 90% accuracy. So it looks sort of reasonably good. and achieve sort of reasonably good probabilities. And what this means is that we can actually now, for newly predicted computational compounds, we can actually assign from this machine learning model a probability with the new compound, that the probability that the machine learning model thinks that it is likely that this compound is going to be synthesized in the near future. Okay, so we can actually go back to the literature and search for compounds where some predicted compounds where the machine learning model is sort of pessimistic about being able to predict that compound in the near future, and others where the machine learning model might be more optimistic. Okay. So I'll just say one more thing before I finish, and that is that this last part of the work, this synthesizability network, was done in collaboration with researchers at Toyota Research Institute. They really sort of took this and ran with it and constructed a materials network website, which is freely available and online. You can go to this maps.matr.io and look at the network. There's different networks. The synthesizability network is one of them. And you can analyze different properties of this. And if you see over here on the right, one of them is, one of the properties of the network is the synthesis probability, which is kind of an interesting way to look at these newly predicted compounds. Okay, so I think I've run out of time. Sorry, I had to kind of rush through the last bit, but I tried to tell you how we can use this kind of large scale database to construct this machine learning, this convex hull of everything. We use network theory to kind of look at the topology and extract information from it, like the nobility index. And then ultimately we use this machine learning approach to actually analyze the time dependence of this network and use that to make a predictive tool to predict the likelihood of material synthesis in the future. So I really kind of want to express that I think that this idea of network theory applied to kind of large scale materials networks is really in its infancy, and I think we've barely just scratched the surface. So with that, I will thank you for your attention and take any questions that you have.